In this section of Unit 2, we're going to talk about more about metals, but also about the concept of an alloy. So metals have that sea of electrons that I've talked about previously. The electrons are considered to be delocalized. So I've added in the picture that I used previously. These are the nuclei of the metal, and then the valence electrons are just orbiting around wherever they're needed. Because of this sea of electrons, it allows metals to have what's called a non-directional bond, which means that those valence electrons can just shift around to wherever they need to. Because of that, when we try to hammer metals or an alloy, as we're going to see in a minute, it allows us to hammer it out into sheets. That's called being malleable. Because when we hammer it, those sea of electrons just shift around and allow us to hammer it out into very thin sheets or draw it out into wire. Even as in the concept of jewelry, we shape jewelry, we're using metals. And so the sea of electrons, that non-directional bond, is what allows that to happen. And then that non-directional bond is what allows metals to be good conductors of heat and electricity, because there's always these positive and negatives available for the energy and electricity to travel on. Ionic compounds, I have a picture over here from one of our previous questions, they are considered to be hard, but they're what we call brittle. And brittle means that they break in areas where there's a weakness. And so the places where that weakness is going to happen is anywhere that there is areas of repulsion. So what happens is ionic bonds are really strong bonds because they have that attraction between the positive and negative ions. But when we hit that ionic compound, it shifts their alignment. So instead of, as we see here, it's that positive, negative, alternating that we've been talking about is necessary. It makes the positives be next to the positives and the negatives be next to the negatives. And when that happens, it is going to break along those areas of weakness. And so we can hammer out into sheets our metals. We cannot an ionic compound. So an alloy is just a mixture of more than one metal. That's all an alloy is. So it is considered to be a mixture, but they're just melted together. There's not a chemical reaction that takes place when we make an alloy. There are two different types of alloys that AP Chem is going to expect you to know. One is called a substitutional alloy, and it's exactly what it sounds like. One metal is going to substitute another metal. Just like if I am absent, I have a substitute who will come in and cover my class for me. And so in a substitutional alloy, what they do is they are going to use another metal that has a similar atomic radius and substitute it into this sea of electrons, into this lattice. And so instead of this being, let's say that this element was gold, instead of being gold, maybe they would add a different element in to help give it some different properties. Maybe they'd add in nickel. So it'd be gold, nickel, gold. And so it would need to be something that is a similar size to the atom. Brass and bronze are really great examples of substitutional alloys. In brass, instead of it all being copper, they use copper and zinc. Those two things are right next to each other on the periodic table, so they're very similar in their size. And the reason the zinc is added is to make the brass have a stronger, be more ductile, and more resistant to corrosion. So we just make those alloys to try to compensate for any weaknesses of a single metal. Copper by itself will oxidize and turn green. If you've ever read anything about the Statue of Liberty, you know that. But when we add zinc to copper and make brass, it takes away some of that resistance to corrosion or even just the oxidation. So then the other example I have of an alloy is bronze. And bronze is copper and the element tin. Sn is the element tin. And so we add tin for the same exact reasons that we did for the zinc. Again, copper and tin are going to be pretty close on the periodic table. And so they do have similar atomic radii. These two are going to be a little bit more different because it's in a different energy level. Copper's in the 4th energy level and tin is in the 5th energy level. But they're still going to be pretty close in size. So that's called substitutional. The other one is called interstitial. And so this one is filling in small spaces in between the metal atoms. So interstitial would, instead of being just alternating like this picture is, it would fill in these empty gaps in here that are available in the middle. And with it, steel is an example. Stainless steel, cast iron, all those things are interstitial alloys, and interstices is a gap in the wall. And so it's filling in that gap. When they add in those smaller atoms to fill it in, again, it is trying to change the properties to make it to be able to be a better alloy, to have different properties. Often it makes it more dense because we filled in those empty spaces. So this is a picture. It tells you that the ion cores, which is talking about the nucleus, is there. And then it shows you that sea of electrons. And it says a particle level diagram of a metallic element is shown above. Typically, metals are both malleable and ductile. The best explanation for these properties is that electrons involved in bonding among metals are, first one is unequally shared and form non-directional bonds, unequally shared and form highly directional bonds, equally shared and form non-directional bonds, and equally shared and form highly directional bonds. So let's talk about what this directional means. So directional is like an ionic compound. We have to have them in certain places. Covalent do the same thing. They have to be in certain places. We'll talk more about that when we get to Lewis diagrams. And so these are going to be considered non-directional because there isn't having to be that same alternating exactly as it is. And you'll notice that the valence electrons are randomly dispersed out through here. But they are equally shared. And so they're just going to distribute these around to be equally shared. And so my correct answer for that one is going to be letter C, equally shared and form non-directional bonds. And then my last question for this section. So steel is an alloy containing iron and carbon atoms, which of the following diagrams best represents the particle level structure of steel. So let's talk about atomic radius again real quick. And remember with it, we have decrease up, decrease across. So iron is in the 4th energy level, and it's in the D block. And then carbon is in the 2nd energy level, and it is in the P block. And so we could say that iron is sort of here, and carbon is up here. If this trend of decrease up, decrease across is true, then carbon is going to be significantly smaller than iron. Iron has 4 energy levels, carbon only has 2. And because of that attractive force between the protons and electrons within carbon's 2nd energy level, it is going to squeeze it tighter and make it smaller. So it's a pretty small atom. So that's what you're looking at up here. You have to think about the atomic radius and then look at my 2 things that I have. Well, I know carbon is not going to be bigger than iron because of the trend, so I can mark out A. I know they're also not going to be the same size because, again, the trend. So then I have these 2 options here. In this one, it shows carbon is 2 different sizes and iron is 2 different sizes. And that's just not even logical. The atomic radius of an atom is consistent as long as it's a neutral atom. When it becomes an ion, the size of the atom might change slightly. But this is saying that they're like significantly bigger and smaller. So that's not it either. So this shows that iron is bigger, which would be true. and that carbon is smaller, which is also going to be true. So this is the correct answer. And then this is an example of interstitial alloy because it has filled in the gaps in between the iron atoms. So with this section, it's pretty straightforward. It's just asking you to understand the concept of what is a metal, what is this concept of sea of electrons, and then it's also often going to ask you to distinguish between the substitutional and the interstitial alloys.